In the last section of chapter 3, we're going to take a look at experimental design. So we're going to spend all of this chapter talking about how to set up and perform a good experiment, along with some advantages it has over an observational study and a couple things to look out for. So there are two key advantages of an experiment over an observational study. One is we can study the specific factors we're interested in while controlling the effects of something called lurking variables. And we're going to talk about these a little later on in the notes. And the second thing is that experiments also allow us to study the combined effects of several factors. So you don't have to just compare two things, you can actually compare three or more things. So when we're designing an experiment, it's important that you have two things. You have to have a factor and then you have to have a level. So in an experiment, the factor is your explanatory variables. So it's the explanatory in an experiment. Then you have your level, and those are the various groups the factors take. Okay. So there is a difference between a factor and a level. So kind of like an example here, if an experiment was comparing three different drug dosages, 50 milligrams, 100 milligrams, and 150 milligrams, the factor is then drug usage, because that's what we're looking at. That's our explanatory variable. We're looking at drug usage. The levels are then the three different dosages, the 50, the 100, and the 150. So the number of levels you have and then your number of factors are not the same thing. So they don't have to match. So like in here, there's one factor with three levels. Okay. So when you are performing an experiment or designing an experiment, there are four key things you want to make sure you are including. So the first one is comparison. So what that means is you want to compare two or more treatments. So, and like in the previous example, we're looking at different levels of drug dosages. So that's two or more treatments, because the three levels that we look at are three different types of treatments. And we want to make sure that the groups that we have that we're comparing don't differ greatly before the experiment begins, or you can have some bias that comes into play. So one way we avoid that in an experiment is through randomization. And there's a couple different ways you can incorporate randomization into an experiment. It is the most important element of any experiment. There has to be randomization at some point. So it can either be incorporated in the selection process of your experimental units, so how people or which are subjects or anything else is chosen, or so you could technically do both, the distribution of those experimental units into your treatment and control groups. And we're going to talk about control groups here in a second. So you can either randomly select people to be part of your experiment, or once you have the people that are going to be in your experiment or your experimental units, you can randomly assign them to different treatments. So a couple different ways you can do this, very similar to what we discussed in section 3. You can use your calculator to do a table of random digit, to do random number generator. You can do a random digit table. You can pull names out of a hat, flip a coin. There's a lot of different ways you can randomize. A couple of key things here though. You can only compare when groups are as similar as possible before the treatment is applied. So you don't want to look at men separately and women separately, because then your groups aren't similar. You would want to have a nice mixture of the two. And then, if they differ afterwards, that's fine. That's where you're going to see how the treatments affected them. So randomization then would produce groups of experimental units that we expect to be similar in all respects before the treatment is applied. And then that way, any measured differences can be due either to our treatment or by a chance of random assignment. It's not based on what group they were assigned to. The third one is control. So in an experiment, it's important to have something called a control group. So a control group is treated identically in all respects to the group receiving the treatment, except the members of your control group do not receive the treatment. So most commonly referred to as a placebo. So that's called the baseline group. And then the experimental group has only one thing changed, which is the explanatory variable. So the main reason to have a control group is to reduce variability in our response variable. So if one group is controlled, we would expect their responses to be controlled as well. And that helps us to actually determine whether or not our results are accurate. The last thing is then called replication, which is not necessarily the definition you would think it is. So we want to make sure that we have enough experimental units in each group so that any difference in the effects of our treatments can be distinguished from chance differences between those groups. So replication here doesn't mean that you have to repeat it or replicate it. It actually means use enough subjects. It doesn't mean repeating. Basically means, did you perform your experiment with a large enough sample? Because even with a control group, there is going to be natural variability between your experimental units, which is why we have control group and replication. So we, as previously mentioned, we want to see all of our units within our treatment group responding similar to one another, but differently from units in other treatment groups. And then that way we can make sure that the treatment is actually responsible for the differences. So if we assign many individuals to each treatment group, then the effects of it being a chance or individual differences averages out. And that way you can actually do a causal relationship. All right, so some very important terms that you're going to see when talking about an experiment. So placebo, something that's used a lot in any kind of medical experiment. A placebo is a dummy treatment. So what it is people think they're receiving a drug, but really they're not. Usually it's like a sugar pill. If it's a pill, sometimes if they're like putting a drug in, it's usually like saline or something that's not harmful to the body. You also have something called the placebo effect. So that occurs when subjects receiving the placebo have a response that is similar to what we would expect if they received the treatment. So it is something that occurs in experiments. People are receiving that placebo, but they report that their symptoms are lessening or they're losing weight or whatever it's looking at. And that's what's called the placebo effect. One way to help limit that is with replication. That way you have a lot more people in each group. That way the placebo effect is minimized as much as possible. We then have something called blinding and double blind. So when you are blinding, which is something that is very important in an experiment, it is when the subject So it is specific to humans, not just anything else. These are specific to when you're using humans. So it's when the subject does not know what treatment they are receiving. So the nice thing about using blinding here is that it limits the power of suggestion. So like if you know that you're receiving the drug, your brain may, or you may think that you're actually starting to feel better. So you kind of skew the results of the experiment into thinking that it's working better. Works the same way with the placebo. If you're not receiving the placebo, you can be like, I don't feel any better. Maybe I feel worse. So it's very important to have blinding when designing an experiment when you have subjects, so when you have humans, because you don't want them to know what they're receiving. There's also a double blind. So it goes one step further. So that's when the subject and the administrator do not know who receives the treatment. So the purpose of a double blind is to then not have any bias from the administrator side. So if they don't know who's receiving what, they can't kind of bring their bias into looking at the results and saying, oh, this is a good enough change for me to say that the drug is having an effect or the treatment is having an effect. So this way they get to look at the data without any preconceived bias and kind of make conclusions. And then afterwards kind of be like, oh, okay, so there was no difference or it didn't perform as well as expected. Okay, so it is important to look at experimental design and some things that could affect it. So the way you design an experiment is very, very important. So way you design an experiment, it isolates the effect of the treatment on the response variable and it removes any confounding effects. Again, something we're going to talk about here in a second. So if you have a poorly designed experiment, what that tells us is that it might be difficult to determine if the explanatory variable caused a change or if it was another variable that was not measured. And we're going to talk about an example of this here in a little bit. So you want to make sure that when you design your experiment, you make sure you take into account any potential variables that could affect the outcome. And then there's something called a confounding variable. So a confounding variable is a variable that might affect the outcome, but was not controlled or accounted for in the experiment. So that's one of those things that could be difficult. That's part of the poorly designed part of an experiment, is that there's some variable that affected the outcome, but you didn't think to control it or account for it in your design of the experiment or in deciding your factors. So one way to kind of remove the effect of any confounding variables, that's where randomization comes into play. So if you randomly assign subjects to your treatment control group, it helps limit or helps lower the effect of any confounding variables. So this way, any possible bias in the population should be evenly spread out among your treatment and control groups. So this is where instead of making the groups as even as possible, we actually are forcing the groups to be similar. So a couple things when we talk about a completely randomized design. So that's an important, that's a type of experiment you can do, is a completely randomized design. That's when the experimental units are assigned to the treatment groups completely by chance. So when you do that, your treatment and control groups will be about the same size. So especially if you have an even number in your population, then they should be the same size depending. Or they might differ by like 1 or 2 people, but you don't want one group to have 400 and another group to have like 100. Those wouldn't be about the same. And then there is a mathematical reason. So there is a mathematical reason to similar size groups. And we're going to be talking about that later. So you want them to be about the same size, and there is a mathematical reason behind this, and we'll talk about it later. So let's go ahead and kind of look at an example. So there was a question that says, does regularly taking aspirin help to protect people against heart attacks? So there was something called the Physician's Health Study, and it was a medical experiment that helped answer this question. So it looked at the effects of 2 drugs, aspirin and something called beta-carotene. The researchers wanted to know whether beta-carotene would help prevent some forms of cancer. And so the subjects in the experiment were 22,000 male physicians. There were 2 explanatory variables, which were our factors. Each of them had 2 levels. Aspirin, yes or no, and beta-carotene, yes or no. And then there was a combination of these levels and factors, and it formed 4 treatments in our pictures here below. And then a fourth of the subjects were assigned at random to each of these treatments. So the way the experiment worked is that on odd-numbered days, the subjects took either a tablet that contained aspirin or a dummy pill that looked and tasted like aspirin but had no active ingredient, so a placebo. And then on even-numbered days, they took either a capsule containing beta-carotene or a placebo. So they were looking at several response variables here. They were looking to see, looking for heart attacks, several kinds of cancer, and then some other medical outcomes. And then they did this for several years, and 239 people from the placebo group and 139 people from the aspirin group suffered heart attacks. So they said that that difference was large enough to give good evidence that taking aspirin does reduce heart attacks. And it did not appear that beta-carotene had any effect on preventing cancer. So you kind of have this table here where it tells you how it worked. So your first factor was aspirin. The second factor was beta-carotene. So you could be taking both aspirin and beta-carotene. So aspirin on your odd numbered days, beta-carotene on your even. You could be taking the placebo for aspirin, but the actual beta-carotene, or vice versa, having the aspirin but the placebo for the beta-carotene, or having the placebo for both. So when it comes to actually designing a completely randomized experiment, we're going to do is we are going to number the male physicians and randomly assign them to the 4 groups. And then that would determine what they're taking. So when it comes to like drawing a picture for this, so you start with your population, which is the 22,000 male physicians. And then we have our 4 groups. And then we're going to label each of these as RA to let us know that they were randomly assigned to one of these 4 groups. So 22,000 divided by 4 is 5,500. So we had 5,500 that received the aspirin and the beta carotene. 5,500 that received no aspirin and the beta carotene. 5,500 received aspirin and no beta carotene. And then we have our 5,500 that received no aspirin and no beta carotene. And then what happened is after our experiment was over, we compared health outcomes between the 4 groups. So when you are gonna describe and design a completely randomized experiment, this is what we mean by design. So the describing is using words. Designing is using the picture. And I find the picture to be a little bit of an easier way to do it instead of the describing, just because it can get a little bit harder to understand looking at all of the words instead of looking at the picture and oh, I know that 22,000 male physicians were randomly assigned to these 4 groups. And then at the end, I compared the health outcomes between those 4 groups. All right. Now we're going to discuss lurking variables and confounding variables in more detail. So an extraneous variable is one that it's not one of your explanatory variables in the study, but it's thought to have an effect on the response variable. And there are 2 of these present in studies. And the first one is a confounding variable. So as we kind of already discussed, that is when another variable may affect the response as in some way tied together with the factor, leaving you unable to tell which of the 2 variables, or perhaps some interaction of them, caused the observed response. So let's kind of look at an example and see how this would play into it. So you're planting tomatoes in a garden that's half shaded, and you want to test a fertilizer by putting it on the plants in the sun and applying none to the shaded plants. Months later, the fertilized plants bear more and better tomatoes, and you want to be able to say, well, it's the fertilizer. But it could also be the sun, or it could be both. So we're unable to conclude that the fertilizer works because any effect of the fertilizer was confounded with any effect of the extra sunshine. So you're thinking about, just like in a picture, you have your more tomatoes, which was your outcome. It could have been caused by the fertilizer, which is what you looked at, but it also could have been caused by the sun, or a combination of the 2. So a better way to do this would maybe, you can still have your tomatoes in a garden that's half shaded, but the half that's in the sun, half of them get fertilizer, half of them don't. Same thing with the shade, half of them would get fertilizer and half of them don't. And that way you can see whether or not it's just fertilizer, just the sun, or a combination of the 2. Then we have lurking variables. So that's when some other variable actually drives each of the 2 variables under investigation, making it appear that there's some association between those 2 variables. So for an example here, so this is more likely to happen in an observational study than it is in an experiment. So confounding variables are more in line with an experiment, lurking variables more in common with an observational study. So we know that there is a strong association between the number of firefighters who respond to a fire and the amount of damage done. We shouldn't necessarily conclude that the firefighters may be responsible for the damage because the lurking variable here is the size of the fire. So our size of the fire is our lurking variable, which then actually affects the number of firefighters who respond It also affects the amount of damage. Because if you think about it, the larger the fire, the more damage there would be. The smaller the fire, the less damage there would be. That also tells you how many firefighters are going to respond. Because if there's a very large fire, they're going to call in lots of fire departments to come and fight that fire. But if it's just a small fire, they'll just call the local station or whoever's supposed to respond and put it out. Doesn't necessarily mean that the firefighters determine how much damage there's going to be in a fire. So as I just said, lurking variables, much more common of a thing in an observational study, whereas in an experiment, lurking variables, which that's where we can help minimize any lurking of variables in an experiment. So let's go ahead and look at some examples. So we're going to look and determine whether the relationship between two variables involves causation, so we can say one of them causes the other, or if there's maybe some type of lurking variable or confounding variable that could be affecting it. So for our first example we have, does TV make you live longer? So what they do is they measure the number of television sets per person, X, and the average life expectancy, Y, for the world's nations. And there is a high positive correlation. So nations with many TV sets have high life expectancies. So we want to know, could we lengthen the lives of people in Rwanda by shipping them TV sets? So in this case, because this is more of an observational study, we know that we're going to have a lurking variable here. So one of the things that kind of determines whether or not you have a lot of television sets and your average life expectancy is going to be money. Not necessarily that you have a TV set, because if you have more money, you can afford more TVs. It also means if you have more money, you can afford health care. So money pays for food and health care, which can help your life expectancy. And if you have a lot of TVs, you probably have a lot of money. Our second question was, do artificial sweeteners cause weight gain? So people who use artificial sweeteners in place of sugar tend to be heavier than people who use sugar. Does this mean that artificial sweeteners cause weight gain? Give a more plausible explanation for this association. So in this case, we're looking at an experiment, which means we have a confounding variable. And the confounding variable here is going to be your diet. Okay. So what that means is people consuming artificial sweeteners could be trying to diet and lose weight. which would mean that they're heavier to start with. It doesn't necessarily mean that they're heavy because of artificial sweeteners, just means that they're already heavier, they're trying to lose weight, so they switch to artificial sweeteners. Third example says, are grades and TV watching linked? Children who watch many hours of television get lower grades in school on average than those who watch less TV. Explain clearly why this fact does not show that watching TV causes poor grades. So this is an example of a confounding variable. And a confounding variable here could be time. So it's not necessarily that watching TV caused them to do poorly, but the trade-off of time. So it could be that students didn't spend time studying, which is something that you could control in an experiment. So if you wanted to see if grades and TV watching were linked, you could control this in an experiment. You could turn this into an experiment and make some kids go home and watch TV, or other kids just go home and study. Then you could kind of say, oh, TV, and then if the people who watch TV still got lower grades than the people who studied, then you could potentially say TV caused poor grades. But if not, then you can't necessarily say that it did. Last one says, to earn more, get married. So data shows that men who are married and also divorced or widowed men earn quite a bit more than men who have never been married. We want to know whether or not there's a confounding or lurking variable in play. So there is a lurking variable here. And that lurking variable is age. So if you think about it, men who are married or been divorced or widowed men tend to be older, which means they've had more experience, which means they make more money than men who have never been married, who typically tend to be younger. So married, divorced, or widowed men tend to be older. So that could be why they make more money, not necessarily. And you got to think, there are some men who stay single throughout their life that do make more money. So you got to take into account how old are these men that we're looking at. Is that a factor in how much money they make? Next thing we're going to discuss are different types of experimental design. So we've already talked about one, the completely randomized design. We looked at an example of that, but it's not the only way to look at an experiment. So the way you design an experiment helps remove any confounding effects, but it also kind of makes us see any conclusions we can make between maybe if we look at different groups. So we talked about how using randomization to make them as similar as possible, but sometimes we want the groups to actually be different. So we talked about completely randomized design. So that's when your experimental units are assigned to the treatments completely by chance. So you have your experimental units, whoever they may be or what they may be. They are randomly assigned to your treatment and control. So depending on how many treatments you have, like you could have multiple treatments, you could have just one treatment, and then your control group, and then you compare the results. Very common, one that we're going to see a lot. There's also something called matched pair. So there's a couple different ways you can do a matched pair. So that's either that the same individual or two matched individuals are assigned to receive the treatment and the control. So either a single individual receives both the treatment and the control, in which case the order in which that happens should be random. And then, or you have two people that are as similar as possible. One of them receives the treatment and the other one receives the control, and then you compare the results. Now, if you're going to do a matched pair, it should be conducted as a double blind. So it does have that kind of added step to it. So the way this works is you have your experimental units individually. So experimental unit 1, they get randomly assigned to a treatment or maybe the control, which means then they get randomly assigned to the control, and then you compare the results. Then you would move on to your next experimental unit. Okay. They maybe get randomly assigned to the control group, which means, and then they're randomly assigned to a treatment group, and then you can compare the results. And then you would keep going for every person that's in your experiment. Third one is a block design. So what you do is you create blocks, and a block would be people who are similar to each other but not similar to people in the other block. And then you have a complete randomized design within that. So it's very similar to a completely randomized design. So you start with your experimental units. They are not randomly assigned to the blocks, they are placed into the blocks. So you've got block 1, block 2. You can have more than one block. You don't have to have two. So there's no random assignment taking place when you assign them to blocks. The random assignment then comes after they're already in those blocks. So you randomly assign them to the treatment group and the control group. And then you can only compare results within that block. So you can't compare the results from one block to another. You can only compare the results within a block. So then for my second block, they would then be randomly assigned to the treatment or the control, and then you compare the results after. Two main things here. So if you're trying to think of when would I block, age and gender are the most common ways that you would block. So if you're trying to determine whether or not men and women would react differently or whether different age ranges would react differently, that's when you would kind of use a block design. There are other ones, but age and gender are the most popular. All right, so let's talk about how we can then make inferences based on the results of our experiment. So an inference is then drawing conclusion. So let's look at two different studies here and talk about conclusions we can draw. So the first one is that the U.S. Census Bureau carries out a monthly current population survey of about 60,000 households. Their goal is to use the data from these randomly selected households to estimate the percent of unemployed individuals in the population. Our second example says scientists performed an experiment that randomly assigned 21 volunteer subjects to one of two treatments: sleep deprivation for one night or unrestricted sleep. The experimenters hope to show that sleep deprivation causes a decrease in performance 2 days later. So when we're looking here, there is a difference in what kind of inferences we're allowed to draw. So if there was a random selection of the inferences, of our individuals, it allows inference for the population. So our first example with the Census Bureau, since individuals are randomly chosen to participate in the survey, they can make an inference about the population based on those results. Whereas if you have random assignment in an experiment, that allows inference for cause and effect. Okay, so for our second example, they randomly assigned people to your two treatments. So if there's a large enough difference in the results, then we could say that sleep deprivation caused a decrease in performance 2 days later. Now, if they were too similar, then we could say that it doesn't necessarily cause a difference. So how your randomization plays a part determines whether or not you can make an inference for the population or an inference for cause and effect. You can make an inference for both. So like we kind of discussed, if you randomly select your individuals and randomly assign them, you could make an inference for the population and for cause and effect. So kind of a breakdown of this. If you randomly selected and randomly assigned to groups, you can make an inference about both. And then it continues on. So the nice thing about random sampling versus random assignment is they both introduce chance variation. So we are kind of looking at the laws of probability to describe that chance variation. And that's something we're going to talk about in chapter 4. We'll talk about how probability plays into a part to look at that chance variation. Last slide here is just talking about the challenges of causation. So there are some cases where it's not practical or ethical to do an experiment to establish a cause and effect relationship, mainly because it's just too dangerous. So texting while driving, increasing the risk of having an accident, is too dangerous. You don't want to force anyone to text and drive and determine if they're going to have an accident, because that could lead to pretty severe car accidents. Does going to church regularly help people live longer? Also, don't want to force religion on people. So another thing, not ethical. Does smoking cause lung cancer? Also not ethical here, because you don't want to force people to smoke who don't already smoke and see, oh, are they going to get lung cancer? Some of these kind of examples are more where an observational study would come into play. If you have data on car accidents, you can look to see, okay, were they texting while driving in their car accident? I can then infer from that texting while driving increases your risk of having an accident. Same thing with the other two. So these might be more better suited to an observational study. So couple things that, so because these weren't regulated when institutions started doing experiments, they now have laws that you have to follow if you're going to be using human subjects. Animals, not as strict. And obviously if you're using food or something like that, there's really not as many regulations. But if you're using human subjects, a lot of laws that have come into play. First is there has to be an institutional review board to look at your results. The board's purpose protects the rights and welfare of the human subjects that are recruited to participate. You have to have something called informed consent, which means you have to understand the risks and can actually consent to being part of the experiment, which is what the next thing is. So you have to be aware of the harm and danger a study could inflict, and you have to be given written permission to participate. And then there's confidentiality. So that protects individuals' privacy by keeping their identities separate from the results. So that's why anytime a drug trial comes out or the results come out, they never release patient names because you have to keep their identities separate. So when we talk about the options for the projects for chapter 3, one of them kind of looks at the challenges of causation. And there's a couple examples here. We'll talk about some others more in detail in class, but these are 5 experiments that were performed in between, like, I want to say the 50s and the 70s, before a lot of these laws were in place, that are kind of seemed the worst of the worst. And there are some few others that we'll discuss as well. So let me know if you have any questions about experimental design, whether that's in setting up the experiment, any of the different methods, confounding, lurking variables, and so on.